Hey, welcome back. This is Professor Roldan once again in Explorations in Math, and we have finally reached our last lesson of the course. This is 12.6 linear regression. Thank God we have made it to the end, and we are going to finish strong here. So this topic is related to something you have studied before, and that is the y equals mx plus b equation, which talks about a line through various points. So when things were perfect, we had points that lined up perfectly. Okay, and we could do y equals mx plus b to calculate slope and y-intercept, things like that. However, what do we do if it's not perfect? So what do we do with data that is not perfectly straight? And that's the question we're going to consider in this section. And so what I mean is, if you have data that kind of goes back and forth, but you can kind of see that this is kind of making a line, but it's not a straight line. But we can kind of draw a line of best fit, sort of in the middle, okay, that represents the general direction of the data. Okay, so this is called a line of best fit. It's the best that we can do, and so we're going to go through a formula that will help us calculate this line. All right, and there are definitely going to be decimals involved. So let's talk about the linear correlation coefficient. The linear correlation coefficient R is something we're going to just talk about so you know what it is. We're going to recognize the different types, but we are not going to actually calculate it, although the book does show you how to do that in a very big formula. We're not concerned with that at this point. So what is the linear correlation coefficient? And it is a unitless measure that describes the strength how strong is this correlation between all the data points? The strength of the linear relationship between two variables. Okay? And so that linear relationship, it could be very strong, which is the strongest positive correlation will be a 1, and the strongest negative correlation will be a negative 1. And right in the middle, 0 would be no correlation at all. So the closer this R gets to 0, the more we can see that these are not correlated. Let me redo that. Okay, so it says scatter diagrams can show the strength of correlation between two quantities x and y. So let's go ahead and go to page 785, figure 12.41, and look at the different types of linear correlations that can occur. Okay, so as we can see here, we have the strongest correlation, which is a positive 1, because the dots or the points line up perfectly. This is what you studied in chapter 6, okay? All right, but that, again, doing experiments and plotting points from a data set are not going to be perfect like that most of the time. So most of the time we'll have some type of, let's say, positive correlation. Here we have a strong, because we could do, you can see how it kind of follows that pattern there. These right here are a little bit more spread out. So this is going to be weak, okay, because they're kind of all over the place, okay, it's a little wider. And this one is going to be R equals 0, okay, because there's no correlation, there's no pattern, there's no form it's taking, it's just a big blob of points, okay, so no correlation there. And now that's the positive version. Now we have the same exact thing for the negative side. Okay, so you can see this is chapter 6 again, where everything is perfect. In the real world, though, we have, hopefully we have some type of correlation there. So that's pretty strong. And this is moderate to weak. I forgot to circle that up there, because this sort of goes down. And then, of course, this one looks like a big blob, which is more of a circle. And this is, again, R equals 0. No correlation, okay? So you just need to be aware of those and recognize, if you ever have a data set and you plotted the points, taking a look at the picture, you could tell if there's a positive or negative correlation, and if it's a strong correlation or if it's a weak or just no correlation at all. Okay, the variables are just not, they're not creating any patterns. Okay. So in the next section, we want to go ahead and draw a strong positive correlation. Okay, so strong positive, not the strongest, because the strongest I've already demonstrated up there from chapter 6. So we just want a strong positive correlation, okay? And then for the negative correlation, same thing, just go in the other direction. Okay? Now, so y equals mx plus b, we're actually going to use that formula, but for the m and for the b, they need to be calculated. And if you study statistics, you can get into the reasoning, and you can get into the proof of where these formulas come from. For now, we're going to trust them, that they were formulated correctly. And so basically, we have this Greek symbol everywhere called the summation. Okay, so this is just summation. To add, it means just to add, okay? To add up, total, whatever you want to call that, okay? So I'm going to call it the sum of all the x values the sum of all the y values, the sum of the x squared values, the sum of the y squared values, and the sum of the xy products. Okay. And n, as you can see here and here and here, that's going to be the number of data pairs. Okay. Now, so we're going to use this formula on the other page. This is just the breakdown of it, but we're going to use an example to get all these values, but this is going to take some time, and you're going to have to use a chart to be able to do this. Okay, so let's get started with page 792. Numbers 19 and 27. These are basically the same problem, but we're going to do 19A only. So notice you see the A there. So 19A basically says to draw a scatter diagram. All right, so first of all, let's copy down the information from number 19, which the x values are going to be 4, 5, 6, 7, and 10. And then the y values from number 19 is 8, 10, 12, 12, and 16. Okay, so we want to go ahead and draw a scatter diagram for those of the data for x versus y. So here's your x. Here's your y, and the x's go to about 10, so we can do 5, 10, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the y values go up to 16, so we can go to 20. So that means half is 10. Half is 5, this is 15. Okay, so we're just estimating here. It doesn't have to be perfect, but now we're going to do our, we're going to go ahead and plot the data pairs. So 4 and 8. So 4 and 8 will be around right there. 5 and 10 will be here. 6 and 12 will be about right there. And 7 and 12 right there, and then 10 and 16 is going to be about right there. Okay, so that is the scatter diagram for number 19A. You got 5 data pairs. Okay, so what kind of correlation exists here? Well, it's definitely positive, but is it strong or weak? Well, it kind of looks like a line, so I would say that this is very strong. Strong, positive correlation. Okay. Now, we're going to use this chart here to help us calculate the slope and the y-intercept from the formulas down here. Okay, so here's the slope, or the m, and here's the b, or the y-intercept. So as you can see, everything we need. So first of all, we need an n. The n is the number of data pairs. So I plotted 5 points. 1, 2, 3, 4, 5. So n equals 5. Okay? Since n equals 5, we're going to put that here to remind ourselves. But as you can see here, I need the sum of all the x's, the y's, the x squares, the y squares, and the product of x and y. So first we need to get those individual values. So for the x squared, we're just going to square all the x's. So let's just go down the line. 4 squared, 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 10 squared is 100. Then we want the y squared. And I can do a different color for the y squared. So y squared is 8 squared is 64. 10 squared is 100. 12 squared is 144. And 16 squared is 256. Okay? And then the product of x and y, you just look at the x and the y and multiply them. So we're going to do basically these two. That's 32. 5 times 10 is 50. 6 times 12 is 72. 7 times 12 is 84. And 10 times 16 is 160. Alright, so now let's go ahead and add up all of these columns. That's going to give us the sum, or the summation that we need for the formula. Okay, so all the x's, put those in your calculator, you're going to get 32. All the y's, add all those up, you get 58. All the x's, add those up, you're going to get 226. All the y's, if you add those up, you get 708. All the x and y products here in the last column is going to be 398. Okay? So the formula basically needs all of these values down here. Okay? So we can cover that up. Alright, so we can go ahead and transfer those numbers down here if you want. So we got 32, 58, 226, 708, and 398. Okay? Alright, so first we're going to calculate the slope. So the slope says n, which is 5, times a summation that we've just found, times minus those two there. We're going to fill in all those blanks. So basically it looks like that. Okay, so we're going to put the sum of the xy's, that's 398. The sum of the x's is 32. The sum of the y's is 58. The sum of the x squares is 226. And then the sums of the x's is 32, and then we need to square that, as you can see there. Okay, so we're just going to take our time and calculate these. So the top part, if you use your calculator, is going to be 1990 minus 1856. The bottom part is going to be 1130, and then 32 squared is 1024. That's going to give us 134 over 106. And if we divide those two, we're going to round it to the nearest hundred, so it's going to be approximately 1.26. Okay. Well, let me circle that instead. Alright, so that m, or that slope that we just calculated for the line of best fit is going to go, we need that right there for the y-intercept. So the b part, we're going to do the sums of the y's minus m, which is 1.26, times the sums of the x's over n. Okay, so we're just going to fill those two blanks with our numbers we calculated from the chart, which is 58 here, and sum of the x's is 32 right there. So we start using our calculators. That's 17.68 on top. Divide by 5, and you're going to get 3.54. Okay, so those are the two values that we need to plug into our y equals mx plus b. So our final answer is going to be y equals 1.26x plus 3.54. Okay. Now that is y equals mx plus b. In the real world, where things are scattered about and not perfectly lined up in a straight line. And that's the whole purpose of linear regression, so that we can actually make some predictions. Okay. So this basically concludes our study in statistics, and just want to point out here for the textbook practice, this is supposed to be 21A. Okay. Don't do it in any of the other parts, because those are requiring you to calculate the R, which is another big formula that we really don't need. We just need to assume that there's correlation, and we can go ahead and find out what is the line of best fit. Okay, so that is it. And if you have any questions, let me know. We're going to be doing some activities like this in class, and so it was a great experiment that we had here, and I hope that that we can continue to improve this type of setup here that we have in the course. So thank you for your attention and for your dedication, and we will see you in class. God bless.